Hi, all this is Miss Biller back, and we're going to talk about the meaning of probability. So, probability is a branch of mathematics that studies the likelihood or chance of a phenomenon occurring. Well, you might ask, what is a phenomenon? It's what you want to predict. That's what a phenomenon is. Okay, like basketball teams winning. When the goats will arrive to eat the weeds. Yay, I love the goats. And when to play the lottery. Believe it or not, you could figure out the best times. All right, so let's look at terms and definitions of probability. So, a random experiment is an unpredictable process. So we are running some experiment, but we're using an unpredictable process, taking our randomness out. Or I'm sorry, our bias out. That's what makes it random when it's not biased. Okay, so the outcome is the result of the experiment. So we would write the probability of event E in a random experiment with equally likely outcomes. So this is the notation for the probability of event E happening. So we would write the probability of event E equals the number of total outcomes of the event E of it happening over the total number of possible outcomes. And I'll simplify that in a moment. Because you know me, I like to simplify things so you can remember. Okay. So we have experimental probability of event E. So that means the number of occurrences of E over the number of trials. And I'll demonstrate that in a moment because that's kind of obscure. So then a theoretical probability formula of event E from happening would be the probability of E is the number of outcomes of the event over the number of possible outcomes. So this is the easy equation. Probability of event E is outcomes over possibilities. Isn't that easy? Why do they make it so hard? Okay, so just remember outcomes over possibilities. All right, let's have some fun now. Okay, so we are going to do some experimental and theoretical probability now. So we have this number cube, otherwise known as a dice, or this singular is a die, plural is dice, but I have one, so it's a die. Or if I don't want to violate any patterns, it's a six-sided number cube. See, it's a cube. Okay, so the theoretical probability of getting a 5. Okay, well, let's look. There's 1, 1, 2, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6 on the 6 spaces. So there's one number, different number on each of these. So if I were to roll this, I would have one possibility out of 6 possible possibilities that I would get a 5. Okay, so that's that. So that would be theoretical. All right, well let's try this. Okay, let's see if I can throw this. Okay, so here we go. Oh, well, there you go. I should be trying to win some money right now. Okay, so I got a 5 the first time. Now let's throw it again. A 4. A 6. Oh, another 6. A 2. another 5. Oh, the 6s are really heavy here. Oh, and the 5s. This is amazing. Oh, I should be. Oh, my goodness, look at all these 5s. My lucky 5 day. 6. Wow, look at it. Oh, there we go. 4. And we're at let's do 20 for a good sample. Well, we finally got a 3. Actually, let's do a multiple of 6. Oh, speaking of 6. Okay, and so we have 6, 10, or 5, 9, 11, 12, 13. So we want 3, I'm going to go to 18. So 5 more of these. Oh, my goodness, look at all these 6s. 3, 1, finally. 5, there we go. So now we have 15, 16. I have 2 more to go. 2, 1 more to throw. 4. Okay. So, oh wait, I went too far. So I have 10. I forgot about that one. So I have 10, 11. Then that was 14, 16. Oh, I'm going to take this 4 off. Sorry for that was the last one. All right, so I have 18. And then I got 5 out of 18. So that would be my experimental probability. Now, if we look at, well, what is 1/6 as a decimal and how close did we get? So I am going to quickly do this. So this one equals 0.17 or 17% of the time. And then 5 divided by 18, well, this one is 0.28, which is 28%. Woohoo! So my experimental probability was much higher than my theoretical. But as my sample size would get larger, this number would go down. Okay, so that's why we want a bigger sample size. Okay, so smaller sample sizes, we get data that's skewed this way, where it's very different from the theoretical. All right, so let's go to cards. Some of you don't know what cards are. So I have a deck of cards. All right, so I did not sort them. Okay, so these are cards. All right, so I didn't sort them because we're going to go mix them up. But it goes from, you have an ace to, let's see, there you go. Show you the different, how it works as far as this, king, jack, okay, and we have ace. Okay, so it goes all the way to 10. So let's pretend I found everything. Oh, here I did find everything. Okay, 5, 6. Okay, so we have a deck of cards. Now, if I had been a really good teacher, I would have gone and sorted out all the 4 suits. Okay, but each suit has this in the suits. Okay, so we go ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, king, queen, king. Sometimes aces are high. Okay, so that's kind of the cool thing with this ace. So it's kind of a valuable card. Now, this is the ace of spades. Okay, and that's a two of clubs. So you notice the little sign here is a little different. And then we have what we're looking for. We're trying to draw a heart. So see the heart? So, and then we have a diamond. So that's called a diamond, an eight of diamonds. All right, so if we look at how many, each of these suits are equal. So let's count how many cards are in each suit. So if this was all one suit, that would mean it's all hearts, or it's all diamonds, or it's all spades. Okay, so let's count them. 1, 2, 3, 4. I'm missing my 5. 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's 13 cards in each of the suits. Okay, so if 4 times 13 happens to be 52. So that's why there is 52 cards in a deck, because there's 4 suits of 13. So, shuffle these cards up so we can increase our randomness, because we're going to pick a card. Okay. All right, now we do an extra couple shuffles like this. I hope some of you are learning something about cards. It's very important. Okay, so theoretically, we just discovered that there are 13 hearts and 52 cards, which 13 goes into both of those, so that's 1/4, which is 25% of the time I should theoretically pick a heart. All right, here we go. Top card. Ooh, ace of spades. 1, 2 of clubs, 2, 8 of clubs. There we go. There's a heart. Queen of spades, or diamonds. So there's one. Okay, so you may wonder, what am I doing? Well, I started just randomly taking a sample. So let's do a fourth of the deck and see how many we get. So 1, 2, 3, 4, 5. And there's another heart, 6. A diamond, 7. 8. Oops, you're not seeing these. 9. Another club. 10. A diamond. 11. A club. 12. Another club. And 13. A spade. So I only did a fourth of the sample of the whole deck. So I have 6, 8, 11, 13. So I couldn't sample the whole deck. Okay, so let's see how my experimental sample worked. All right, so I had 2 hearts out of 13. All right, so let me quickly figure out what that decimal is. So that's 0.15. Now approximates. So that's 15%. Oh no, that's very different than this one. So my experimental getting a heart was much lower than my theoretical. And I only did a fourth of the population of my deck of cards, because I only did 13 out of the 52 cards. So if I did half of the deck, I should have gotten a better answer. Okay, if I did the full deck, I would definitely get 25%. So you see how sample size makes a big difference when we're doing experimental probability. When we have a bigger sample, this gets much closer to our theoretical probability. All right, So let's go with the next one. You might like this one. I spilled a bunch of M&Ms all over my pantry, so thank you for giving me a reason to clean them up. So, all right, so we have picking an orange M&M, and we have a theoretical probability. So I counted all these M&Ms that were spilled. Okay, so let's go over the theoretical probability. So I had 11 yellows, 18 orange, 26 green, 12 brown, 7 blue, and 12 red. So when I added them all up, I had 86 M&Ms. So when I wanted to find how many orange M&M, or the probability of picking an orange M&M, that's 18. So I put 18 over 86. Then I divided both of them by 2 and got 9 over 43, which is 0.21, or roughly 21%. Okay, so this is how you would do it the hard way, doing long division. Remember, top dog in that. Okay, so our theoretical probability is 21%. So let's put that here. 21%. All right, let's see. So I got my bag of M&Ms. I am not looking. I'm really not looking. Seriously, I am not looking. Okay, so there's one green. Okay. Let's see. A red. A brown. A green. Oh, there's an orange. So we'll pick 20. Okay, and I'm grouping them in 5s to make it easier for me to count. 1, 2, 3, 4, 5. Ooh, those greens are pretty predominant. 6. Okay, so there's a group of 5 and a group of 5. 7, 8. Oh, another orange. 9, 10. Okay, so one more group of 5, and we'll see what we've got. 5. Okay, so, oops, well, we'll just do that. 1, 2, 3, oops, yellow, brown, and a yellow, and I need one more. Green. Okay, so let's count them, make sure I've got them all. So I have 7, 8, 11, 13, 16, 20. All right, so I have, out of this, I have 2 oranges out of 20. So I have 1/10, which is 0.1, which is 10%. So my theoretical probability was 21% versus that. Should we get in some more and see if we can get closer? Oh, okay, we will. So let's try this and see if we can get closer. Okay, so I have a green. We'll use a different color so we know our other stuff. So we have another green, another red. Oh, there's an orange, yellow, orange, green, green. Okay, so there's a flower. and then a blue, green, brown. And let's start another group of flags. One. Oh, those greens are really popular there with the picking. Okay, one brown. There's another orange and a blue. One yellow. Let's see. There's a red. Oh, another orange. A green. Another green. And one more. Oh, blue. Okay, so let's look at this probability now. So we have 20. We have 40 now. So we have 20 plus 20. Okay, so we have now 5. Okay, oops, no, there's 1, 2, 3, 4, 5. So there are 5. So our experimental probability with 40 versus 20 in a sample gives us 5 over 40. So that's 1/8, which is 0.125. So that's 12.5%. So we are approaching this 21%. So we're getting a little closer. So the bigger the sample size, again, the closer experimental probability we'll get to theoretical probability. Okay, so these two get closer together the bigger the sample size. All right, so that's it. I hope you had some fun with all my sticky M&Ms and cards, and I hope you have a wonderful day. Bye.